when I arrived at Tel Aviv airport, I still needed a ticket to get to Haifa. So I bought myself a Ravkov card and charged a ticket on it. But since it's the first time I'm in Israel, I didn't know where to go next. So I asked the ticket lady where the train station is. And she told me the direction. She told me that I need to go through the elevator to platform 2 and that the train will depart there. And I have roughly 5 minutes to go. So with all my luggage, I thought that's a nice challenge. I went there, went to that direction, had a little chat with the security guard, went down the elevator, saw platform 2, saw the train waiting there, jumped into the train, and eventually the train took off. Only 30 minutes later, I arrived at Jerusalem.
Yeah. So, you were lucky, they get stuck quite a lot.
But yeah, so what went wrong? Since the lady told me I had only 5 minutes, I completely tunnel visioned. I knew I had to go in that direction, elevator, platform 2, train, and I didn't look left or right for any further options. And I think this is the same in life, in many domains. I find myself quite often following one specific idea, trying to implement that, not looking for other approaches, just solving the problems I encounter with this idea. And fortunately, while I was preparing a topic on SSDs, I found that this happens to other researchers quite often as well. For code classification SSDs, for example, all share the same basic idea. All of the papers I read share the same basic idea. They count the accesses to the logical page, and the more frequently it is written, the hotter the data is classified, and vice versa. And then they try to port this idea to SSDs. When looking at SSDs, they find they have a very limited processor and a highly limited amount of DRAM. So they follow the same approach. They implement the data structures in the DRAM to approximate the number of accesses per logical page, because having all counters in DRAM just doesn't fit there. So the approximation is a good way to go. But by doing so, like me, not looking left and right, looking for the train label, for example, they didn't look at the huge amounts of flash memories we have by now. By now, SSDs have up to terabytes of flash memory. So in this talk, I'm going to argue that we don't need the data structures to approximate the access counters. We can incorporate the hot-cold classification design into what flash memory already gives us. And use the good properties of flash memory and use the algorithms that already run in the firmware of SSDs to update the metadata we need. And by doing so, we will get the exact values for the access counters, no more approximation. Therefore, we can improve the classification quality, and a really nice feature, to be honest, by storing all our metadata on the flash memory, we can become independent from DRAM. So we will not use the DRAM as a requirement for our algorithm. We will use it only as a bonus to our system, only as a bonus to speed up our classification. And so we can also run on highly limited devices like what we saw earlier in the conference, that we have highly limited amount of flash chips in our mobile devices. Not a lot of DRAM there. We can also manage these ones. So to do that, we need to take a closer look at how flash memory is actually designed. And whenever we write data, we write to flash pages. And to be more specific, we actually write not only the user data we were sent, we also write some metadata for that page. For instance, the error correction code and the logical page number for the data that is written in this page. And I'm going to argue that the spare region is actually the perfect place to also store additional information for the classification process. To do that, for instance, we can shrink the error correction code a little bit and therefore fit it into the spare region we already have in our device. Or we can also simply talk to our flash vendor and just ask for a greater amount of spare region. Because they produce it, they can provide us with what we need. So let's see why this is actually such. I'm going to argue that this is a good approach. Let's take a look how all of this actually incorporates with the design of SSDs. Given we have already a dirty device, we wrote some data, we classified it in hot and cold, and now we want to update the data that is written to logical page number 23. So, since our access counters are written into spare region, we first need to read the spare region from the access counters. We need to read the access counter from the spare region. Then we increase the access counter by 1, for instance. And then we can rewrite our data. But since flash memory cannot update it in place, we need to write it to a new location. And the old location becomes invalid. Well, I can see by your views, having one read for every write is a high overhead. And again, we don't want to tunnel vision, and we want to use everything we have. So we will also use the DRAM to implement a cache there. So whenever we write data, we first check the cache if it already contains the access counter for that logical page. And so we can do also for logical page number 44 and 45, it will be served by our cache, and we can write it to a new page. So, fortunately, this example has hit the case where our SSD needs to get rid of the outdated data that accumulates over time in a log-structured approach. And to do so, it needs to erase, unfortunately, an entire flash block. But the first flash block cannot be erased since there's still valid data in the first page. So, logical page number 22 still contains valid data, and it needs to be moved first to a new location before we can erase it to prevent data loss. So, and here's where we interfere again. When the garbage collection process needs to move the data, it needs to read the entire flash page, including the spare region. And then we will also, so we get this read basically for free. We can decrease the access counter by 1 to also implement a decay process over time. And once it is written to a new flash page, the old flash block can be erased. And actually, this example was really nice for the garbage collection process because it only found one valid page in a block. In reality, this is much more heavy in the background process. So even though Ying already presented why hot code classification is so helpful in SSDs, I still want to give you one slide about it. Just assume 2 use cases. One where we have data separation according to hot and cold, and one where we don't. Now, hot data is written to a new block, which is not shown here, and the old locations become invalid. Now, in the first example, the garbage collection process just can find a block which it can erase. In the second example, we have a lot of mixed blocks where a lot of valid pages still remain in the flash blocks, so more blocks need to be moved over time. Let's summarize our approach here. First, we now store the access counters in the spare region of each page. We don't store it in the DRAM anymore. And we increase the access counter whenever we write to a logical page. We decrease it when the logical page is moved by the garbage collection process. And we use the DRAM only as a cache and not as a requirement anymore. And also very important here, we do not introduce any additional writes by doing so. We will only introduce additional reads, which are very very SSD friendly, because they don't trigger the garbage collection process and so on. And the number of writes will remain the same from the user. So even though we now have the access counters in place, we still need a threshold to specify data as hot or as cold. And unfortunately, what we found is that a lot of related work still relies on some static thresholds. So we need to analyze the workload before running them on SSD to get the optimal performance. What we want to do is, we want a self-reliant threshold within our SSD, adapting to the current workload. And a very simple idea to start is just taking the average among all access counters. But we quickly noticed that this has a few flaws. Right? If we calculate the average in this example, we end up having hot and cold pages, but also hot pages which are accessed only 30 times. And they are classified as hot even though 30 is much closer to 20. But just by the logic, it should be classified as cold. That's because we also take into consideration all the unused blocks which have an access counter of 0. And now consider a second use case. If all the data that was written previously becomes static, which means the workload ends, and we run a new workload on that SSD, all the old values still influence our new workload. So the new workload is classified as cold for a long time, but we want to be more adaptive. So let's see how we can modify the average so we can kind of work that out. Well, first, we do not divide by the number of total pages anymore, but we divide by the number of used pages, which kind of helps us with the first problem. To become more adaptive to the current workload when the old data becomes static, then we also subtract a fraction of the current average of the current threshold value, and though we kind of defined a fading average, just as a first example to what we can do with the exact values. And even though if I said that we classify everything above the average as hot and everything below as cold, we ended up implementing multiple levels of classification. So for the first level, everything below the fading average is classified as cold, but the more accesses the pages gather, the hotter the data becomes. And the reason is why we use exponentially growing thresholds is that the hotter the data, the less pages are accessed. And we kind of want to balance that out. So let's take a look at how we evaluated our system, because even though we are now independent from flash memory and we have a self-adapting classification threshold, we still want to keep up with the results of the related work. And for that, we implemented SSD simulator, which we have configured with 950 gigabytes flash memory, and we equipped it with 326 megabyte DRAM for the classification process. Even though this is only one configuration I'm showing you today, in the paper we have more configurations, more DRAM configurations, and where we also evaluate how the different algorithms adapt to having more or less DRAM. And we further used 7% overprovision. Then we ran a warm-up phase on the simulator to ensure that all pages are written at least once before starting our trace files. For the trace files, we ran first an SPC1 workload, the data of which then becomes static after a time, and then we run TPCC afterwards. So the challenge here is the classifiers first need to adapt to SPC1, then they need to notice that the data of SPC1 becomes static, and then they need to adapt to a TPCC again. And today I'm showing you only the total number of I/O operations. We are comparing our classifier, FADaC, against one of the second-best classifiers from the related work, two-level LRU. And first we take a look at the additional read operations we are introducing to the system. But we see that actually we have a lot of cache misses and increase the number of reads by 26%. But on the other hand, we also decrease the number of writes by 32%, which in total makes minus 8% in the number of total I/O operations, just by having the exact access counters. So let's summarize what we did here. Yeah, and of course the paper has more results and more aspects which we analyzed. So what are the main findings here? First, we do not have the access counters in DRAM anymore, so we become independent from the amount of DRAM our system has, which also enables us to run on mobile devices. And then we manage the access counters when the flash memory needs to touch them anyway. So whenever we write them, we increase them by 1. Whenever the garbage collection process reads and moves them to another location, we decrease them by 1. And we also found a self-adapting classification threshold to either classify them as hot or as cold. Thank you.
We have time for a few questions.
Yes, please.
Yeah, about the way you handle the counter. So on Nexus you increase by 1, but why do you decrease by 1
during the garbage collection?
Yes.
Yeah. So the question
let's
is...
say I have, for example, access counter of, let's say, 100, and then the garbage collection reduce me by 1, and then I increase by 1, and I will always be 100, even though my current rate is like of access is 1 per garbage collection.
Well, yeah. This definitely might happen, yes. But though I haven't really debugged the individual counters, though the idea is to decay them over time once they become static. The data is not touched anymore.
So you need a decay function that will converge to the right frequency.
Yeah, but in your case, the data is still accessed frequently, right?
Not that much. For example, one counter has an initial value of 1 and the other has an initial value of 100 because something that happened before. And now both of them are accessed only once per garbage collect. So they retain this value indefinitely, and you can distinguish them.
Actually, I'm fine if they come into a static state, like +1, -1, +1, -1. Well, the idea is that it would be actually more problem if we can't decay them fast enough. But the decay process is actually there to if they become totally static. But if they're still active, then usually it worked. In our examples, it worked quite well that they have they're continuously updated, as in your example. Yes, please.
If I have a flash flood that's homogeneous and that it all becomes static at the same time, it was all hot. So I'm never garbage collecting that. I'm never changing the counters.
Totally fine. Well,
Then it starts being used again, it's going to show up as hot, even if it's not being used heavily in the future?
Then it will show up as hot, yes. But the question is it going to be in one workload or are they two different workloads? If it's two different workloads, I would expect the user or the operating system to have a trim operation in between. And when you experience a trim operation, then you can also just reset the write counters to 0.
And if it's one workload, but the intensity of the usage is different at different points in time? So it's,
then that's definitely a problem, but again, I haven't experienced this in my trace files. If you can provide me such a trace file where this occurs so frequently that it becomes a problem, I'll be happy to add it to my evaluation.
More questions? Thank you.